So starting with the one sample testing of hypothesis means if we have a single sample means we have a single variable, or you can say a single factor with respect to a single factor variable. Like for example, if I want to compare somebody's claim that the production cycle time is 3 minutes, and I want to test that particular claim. Or if I am saying teacher is claiming that my class marks is on average 90, and I want to check that claim. So that is basically the single sample testing of hypothesis. And we can start with a single sample means when we are comparing a single mean, or you can say a single sample to a specified value. A single sample means that is a single variable's mean, and we are comparing that mean to a specified value, like as I have given the examples of marks, like class marks, that the teacher is claiming that on average the class marks is 90, and we want to compare that is the class marks on average 90 or not, is that claim is right or wrong. So for that we can apply mainly theoretically speaking 3 kind of tests depending upon the condition, but like the condition is like we want to test the mean if the distribution is normal because it's a parametric, and the population standard deviation is given, so we can apply z test. Okay, and then if the sample size is greater than 30 but population standard deviation unknown, still we can apply the z test. But if the population standard deviation is unknown but the sample size is less than, then we can apply t-test. So this is theoretically speaking, but practically speaking, so whenever the population standard deviation is unknown, so we can apply the t-test. But right now, as we have discussed this selection of the testing of hypothesis in the previous lectures or in the previous videos, so right now I'm just applying, I'm going to discuss how we can apply the one sample z-test using R. So the example is, so this example we have already discussed using the mini tab, like we were talking about the breaking strength of a fiber to be at least 150. Okay, and the past experience indicating that the population standard deviation was given, so we can apply the z-test over here, and we have taken the observations of 4 sample size we have taken, and we want to test at level of significance 5%. So from the above statement, so we develop the null and alternative hypothesis as it is written on at least. That means 150 is included. So we will first develop the H0, and opposite to that one, that is the H1. So this is a one-tail test, right? It's a left tail. You can see the left tail distribution, right? So, but how we can apply this in one sample z-test using R? So remember that the population mean is 150. The population standard deviation was given, which is 3, and the data set was this. So when I am using R, I'm hoping that that everybody's understand the you can say about the R Studio as well as R. So if you don't have the understanding about this R Studio, so you can watch my videos on probability and statistics about the introduction of the R. So right now I'm assuming that you are familiar with the interface of the R as well as R Studio. So I am just starting how we can perform the one sample z-test using R. So starting with like we have given the data set, that is this one. So we have the 4 observation. So in R, I'm going to define a vector which having these 4 values. Okay, so that means X is a vector, or you can say is a variable in which I am assigning these 4 values as a vector. So C is a concatenating, or you can say combining these 4 numbers as a vector, right? Or you can say as an array. And first thing with what I am doing, I am collecting some descriptive analysis. Okay, mean the first thing, the length function, what it will do, it will just give me the counting of these numbers. So right now I'm saying length x, that means count how many values are available in this variable. So if I run this value, so right now x, and if I write down x over here, so I can see all those 4 numbers, right? So I can also access each element, right? If I am writing down x2, so I will get the second position element, right? But right now, first of all, I want to know how many number of values are stored in the data set x. That is n, length x. So it is giving us 4, okay, because it's the 4 numbers. So if I want to compute out the mean, how can I compute? So I am just using the function mean and the name of the variable in which we have stored the data, and I'm storing it into the variable called AVG. Okay, so that is average. Then I'm calculating the standard deviation. The function for that is STD. Okay, so here I'm computing the standard deviation, because in the problem they have given us the population standard deviation. So for that I'm using that population standard deviation divided by square root of n. So this is called as standard error. So I'm computing the standard error and storing into the variable called SE. And then now I want to report all in one way. Okay, mean I want to know how many number of observation is there, what is the average value, what is the standard deviation, and what is the standard error. So for that I'm combining that. So this is C combined. So C bind function will do combine, column combined. Okay, mean it will binding all in a column wise. So it will write down, if I run this, so I will get n is equal to this, average is equal to this. So I can also use R bind. So if I use R bind, that means row bind. So that means the reporting way is different. So now I can see n over here, average over here. Wherever in C bind, so it is giving n average at the upper side, and the values are downside. So it's up to you how you want to see the data in a reporting. So in a C bind, it is column wise combining the data. So now I am getting n as well as average, standard deviation of the data as well as the standard error. So the next thing, because I want to apply the one sample Z test, so I need to compute the Z statistics. And the formula for that is, you may know that the Z is equal to x bar minus mu divided by standard error, or you can say sigma over square root of n. So right now, what is x bar? That is the mean of x, which we have already calculated as well. Minus 150, that was given in the problem. So divided by population standard deviation was given 3, and then square root of n. So with the help of this, we have calculated the Z statistics, so Z statistics. So once I run this command, so it is calculating the Z statistics. Again, now the value of the Z is minus 0.83. Okay, so that means if I draw a standard normal curve, so it would be look like this way. So that means we know that in a standard normal distribution, mean is always equal to 0. So this value is minus 0.833. Okay, so this is Z at the left side because it is less than 0. Right, G? Okay, so the next thing is, now I want to find out the confidence interval as well as I want to find out the p-value. So in order to compute out the confidence interval as well as to compute out the p-value, so we need a package called distribution. So you know how to install the package of the R. So you can go to the package, install, and then you can find out distribution 3, and then you click on the install button and make sure your computer is connected with the internet. So once you install this package, then you need to call it. Like for calling the package, you can use the function called library. So we call it, and then we are calculating again calling the standard normal distribution. So we are saying Z is equal to normal, the mean is 0 and the standard deviation 1, because the standard normal distribution is 0 and 1. So we are saying Z is a standard normal random variable where Z is equal to from a normal distribution where mean is 0 and sigma is 1. Okay, so now the value of Z is, so we have the value of Z is, sorry, because it's a capital. Okay, so then the value of Z is basically, it comes from the standard normal distribution with mean 0 and sigma is equal to 1. Okay, so using this particular distribution, now we are calculating the confidence interval. Because this is the one tail question, because in our one tail mean, the problem was our H naught was mu is greater than or equal to 150 and H1 is 150. So when we are going to calculate the confidence interval, so we are calculating confidence interval basically the upper side confidence interval, mean upper confidence interval. Okay, so this one. So that's why in R, what I am doing mean plus. So this is indicating the upper confidence interval. Okay, so the formula for this is actually what I am doing, X bar plus Z alpha by 2, or you can say Z sigma over N under root. So this is upper confidence interval, right? And that's why plus. And Z, how we can calculate the Z alpha by 2 with the help of this function, that is quantile the value of Z comma, so this is the probability. So that is because I am finding at 95% confidence interval, so that by 1 minus 0.05. Oh, sorry, so the mistake I have done over here is there is no alpha by 2, only Z alpha, mean X bar plus Z alpha sigma over N. Okay, so this is the upper confidence interval. So this is the Z alpha value and then sigma over square root of N. So with the help of this, I will get the answer of upper confidence interval. Okay. Now again, what I am doing using the same function C bind, mean column binds of N, which we have already calculated, average value of the data, standard deviation of the data, standard error, as well as confidence interval, that is CI. So if I run this button, now I can see how many data points in the data, that is the 4 number of observation, what is the average value, what is standard deviation, what was the standard error, and this is indicating the upper confidence interval. So even we use this to inference about our population. So the inference is the population mean is less than 150. Okay, so if the population mean is less than the upper confidence interval, because right now our population mean is 9 in the confidence limit range, because the upper confidence was 150, 1.2173, and the population mean was 150, and this region is called as acceptance region because the population mean is lying within the acceptance region. So we will say accept H naught. So accept H naught, that means what? That means that the breaking strength of a fiber is at least 150. So that means it would be 150 or more than 150. It cannot be less than 150. Okay, so that's accept H naught. The other way is we should use the p-value to make the decision. So how we can calculate the p-value? So right now I'm using the p-value as a variable, is assignment operator. CDF is a function which is called as cumulative distribution function of what? The variable Z, that is a standard normal random variable, comma the value of Z, which we have already calculated. Okay, so from over here using this one. Okay, so if I use this one, so I'm getting it, using Z statistics. This is basically the table. So using Z statistics, using this form, which is this. Okay, minus 0.833. So using the Z statistics. So that is the Z, comma, the Z statistics value. So that means we are basically talking about this. If I draw a normal curve, the mean is 0, where C is equal to 0. So this is minus 0., and we want to find out this value, and this is equal to basically the p value. Okay, so we want to compute out this probability. So how we can do that? So we can use CDF, cumulative distribution, from Z, comma, the value of the Z statistic. Okay, so we run this command and then again run this command, and the answer of the p value is 0.20. Again, we would say what's the decision making criteria using the p value is, if the p value is greater than or equal to your pre-decided alpha value. Okay, so right now we have, because we consider 95% confidence interval, that means the alpha value we have taken is 0.05, is greater than or equal to, what is the p value? 0.2032. Because this condition is true, means p value is greater than or equal to alpha value, so we will say except h. And what was the h naught? That is the mean breaking strength is greater than or equal to 150. I hope it's clear how we can perform the one sample Z test using R. Now we are going to apply one sample T test using R. So the data which I am using is this one. That is basically the shelf life of the carbonated beverages, right? And we have taken the life of those carbonated beverages in days, and we have taken the sample of 10 days data set, or you can say 10 bottles data set, and the H0 and H1 would be equal to, that is basically, again it's a one-tail test, and we can develop the H0 or H1 because it is writing exceeds 120. So your H0 would be equal to mu is less than or equal to 120, and H1 would be mu is greater than 1, right? Because this particular number is not included due to only exceed, so that's where we first develop the H1, that is greater than, and the opposite to that one, H0 is less than or equal to. So this is one tail test. So the mean population mean value is given, so there is no population standard deviation, so we can apply one sample T test. Okay, and the data set was given. So how we can apply this this test using R? So the first thing what I am doing, I'm calling a package called mass. Okay, so that is built in. So you can just write down mass and library and in bracket mass. Okay, and then I am defining a variable called day, and all the data set I am storing in that particular variable, which is day. Okay, in R there is a function called summary, which will give you the basic descriptive analysis, like what is the minimum value in the data. Okay, what is the first quartile of the data, median, mean, third quartile, as well as the maximum. So if you want to find out the mean at the standard deviation, you can use the function mean and then the standard deviation. So this is basically the descriptive analysis. But right now, with the help of these functions, I am also checking the data with respect to different graphical representation. So first of all, this line of code is basically, you can say, designing the layout of a page. Okay, that is basically the par function is basically using to partition the page, and m row means basically we are distributing the frame row wise. Okay, and how we are distributing the page, that is 2 by 2. That means 2 rows, 2 columns. So first I run this command, and then I'm running a command called plot day. So that day is a variable plot. So what this command will do, it will just draw a graph in which on x-axis you will see the indexes, mean the number of values. On a y-axis it is showing actually the actual data points. Okay, So the first data point, what's the value? The second data point, what's the value? But the second is we are drawing the histogram. Okay, in order to understand is the data is symmetrical or not. Okay, as this is a descriptive approach, so we can't say exactly is it look like a symmetrical or not. So another tool is we can use the QQ plot. Okay, so in QQ plot we will see on x-axis the value of the standard normal variable, which is z. On y-axis we are using the actual data set. If that data point is exactly the linear, like we can draw the QQ line as well, which is basically the normal line. If all the data points are lying on this particular line, then we will say data is normally distributed. If the data points are far from this line, then we will say data is not normal. Again, this is a you can say a descriptive approach. We cannot 100% get the idea is the data is normal or not, but we can make some hypothesis by seeing this. It look like the data is normally distributed. So we can also draw a box plot, okay, to understand what's the center value and how much the outline. So this is basically just the graphical, you can say, representation of the data set. In order to clearly get the picture is the data is follow the normal distribution, so we need a package called NOR test, that is normality test. Okay, so again you can install the package NOR test, and once you install it, then you can run this library. So because I'm calling the library, and the test I'm going to apply is AD.test, that is basically the Anderson-Darling test. So if I run this test, and I'm showing that Anderson-Darling normality test, and the p-value is 0.6061. Okay, so in such case, if the p-value, which is right now in this case is 0.6061, is greater than or equal to alpha value, okay, which is the case of over here, because alpha value, if we are assuming 0.05, so we will say accept H0. Okay, so in such normality test, what was the H0? H1 is data follow normal distribution, right? Whereas H1, what is H1? Data does not follow normal distribution. Okay, so we are saying except H0, that means data is normally distributed. So this is the way we can check is the data is following the normal distribution or not, because this is a pre-assumption for one sample t-test, that if you want to apply the one sample t-test, your data must be normal. Another way to check the normality is we can apply the Shapiro-Wilk normality test. Okay, so in order to do that, we can use this function Shapiro.test. So again, for this test, as well as the p-value is greater than or equal to the pre-decided alpha value, so we will say the data is follow the normal distribution. So once we confirm that the data is follow the normal distribution, that means we can apply the one sample t-test. So in order to apply the one sample t-test, so the function is t.test, then the name of the variable in which we have stored the data, which is day, okay, comma, then the value of the mu, mean the population mean value, which is 120 is given over here. Okay, so we store 120, and then what is the H1? That alternative mean, what is the H1? So we develop the H0 as well as H1, because it's writing down exceed. So H1 would be, mean alternative would be equal to mu is greater than or equal to 120, whereas H0 would be mu is less than or equal to 120, or you can say equal to 120. So that's why I'm writing down alternative is equal to greater. Okay, if it is less, so we can write simple less. If it is 2, so you can simple write down 2 dot cited. So if you don't mention anything, so by default it will consider as a 2-tailed test. So by right now it's a 1-tailed test, so that's why I'm writing down greater than. So if I run this command, so I got one sample t-test results, and the t-test statistics answer is this one, but for result concluding this is the p-value. That p-value is 0.0544, which is greater than or equal to your pre-decided alpha value, which is 0.05. Again, we will say except h0, but p-value is almost equal to the pre-decided alpha value. So we can also say that we cannot 100% be sure. So we may need more data set to make the accurate decision. But by the way, with the given data set, we can say except h0. Okay, but type except h0. And except h0 means the shelf life of the bottles is less than or equal to 120. It cannot be greater than 120. But practically speaking, we need more data set because the p-value is almost equal to the alpha value. Okay, so here I am giving another example for one sample t-test for the same thing. Okay, but the data set was the different, same the data values I am storing into the values, checking the normality. Okay, so data is follow the normal distribution, and same plots we are drawing. Okay, and getting the t-test. Okay, right now the mean value in this data set was p, and it's a two-tailed test. That's why I'm skipping this. Okay, I hope you have clear what how we can apply the one sample z test as well as one sample t test. Now we are moving towards if we want to apply the one sample sigma test, like means that is a chi-square test. So if I want to test is the population variance is equal to the target value or not. So for that we can apply the chi-square test, and we have already discussed this example using Minitab in the previous video. Now we are going to discuss with R. Okay, so the population variance is equal to 1, and the question is the manager of lumber yards want to assess the performance of the sawmill that cut the beam, okay, is supposed to be 100 centimeter long, and the variation they have measured and the sample size they have taken, that is a 50 beams, and they want to check is the population variance is equal to 1 or not. Okay, it's a two-tailed test. So what I am doing, instead of creating a vector, so I already basically store this data set in an Excel file. Okay, that is the beam length. Okay, so now we are going to see how I can read this Excel file using R, and then how can I use this data set to analyze the chi-square. So this is a data set, and this is 50 samples, and this is the value they have given us. So now I am going to first of all read this data. So in order to reading it, mean attaching it, first of all what I need to do, I need to import this data. So one of the way is using the R Studio. We can go to this window, environment history connection, and if I click over environment, I will see import dataset. Okay, because the Excel is the extension was the Microsoft Excel, so that's why we will click on Microsoft Excel. If you want to read the CSV file, then you can click from text reader. Okay, if it is only a simple notepad file or a text file, then you can use this one, or SPSS file, SAS file, or startup file. So right now I have an Excel file. I will click over here, then browse. Okay, so my data file is in the folder of R. So this is the beam length, right? If you can see that as soon as I have selected that file, so R Studio I have written down a code for me. So they call the library, whatever the library I needed. They read the data set, and they also run the command of view. However, we can see the data values. Okay, so I'm saying import. Okay, so they run all the commands for us, and we can see the data set. Okay, if I just cross this data set, I am now back to this. Now we have import data. that data set. Now we can use that data set. In order to do that, we will run a function called attach. So attach beam length, that is the name of the data file, and make sure there is no space between the name of the file. Okay, like beam, we cannot choose beam space length. So you should write down without space. So attach beam length. Now the file is attached. Now I want to apply the one sample variance test, that means chi-square test. For that, I need a library called, or you can say package teaching demos. So I already installed, I'm just calling it library. And then the function which I can use in order to run the chi-square test is sigma.test. Sigma.test. Then the name of the variable, name of the data set $length. If I, because I attach this data file, if you don't use this data set as well, only write down the length, then this is also okay. Okay, but what this command will do, this will, the name of the data set, dollar, whenever using the dollar after the data set, that means we are calling the column name. So what is the variable column name? That is a length. Okay, and then we are writing down sigma SQ. If you want to test the variance, then you need to sigma XQ. Okay, if you want to test only sigma, then just write down sigma. Okay, so right now the variance value was 1 that was given. Okay, so the variance is 1. And then the alternative is the two-tailed test, and we want to write down at 95% confidence level. Okay, so if I run this command, and this is one sample chi-square test for variance, and this is indicating the p-value is 0.215. How we will interpret it? This p-value is greater than the alpha value, so that means except H0. And what was the except H0 means? That means the population variance of the sawmill is equal to 1. It is not less than, or it is not greater than 1. It is exactly equal to 1. I hope everybody is clear about one sample test with respect to mean, one sample z test, one sample t test, as well as we have discussed the assumptions of t test, that is a normality. And then we check how we can apply the one sample variance test, that is a chi-square test. For that, the data must also be the normally distributed. So you can also apply the normality test. Testing of hypothesis for two independent samples with respect to the means as well as with respect to the variances. So first of all, if you want to test the difference between the two means and both the samples are population and the population standard deviation are given, so then we can apply the z distribution, as well as if the sample size is large enough, then we can apply the z distribution. Both the cases in real scenario it's quite tough, but that's why most of the cases, whenever the population standard deviation was unknown, whatever the sample sizes are, we can apply the t distribution, or you can say the t test. But in order to apply the t test, so there is a two main condition we need to fulfill before applying the t test. Number one is both the samples must follow the normal distribution, and the second thing is we need to check is the variances of the two samples are equal or not equal. If there is an equal, then we will, by assuming equal variance, we will apply the two sample independent t-test. If the variances are unequal, or you can say not equal, then we will apply two sample independent t-test with unequal variance, which is also known as Welch approximation. One more thing, when we are talking about we want to compare the two groups, that means you are interested into comparing the performance of the two shifts with respect to the production rate. The production rate is equal in shift A as well as in shift B on average. You want to compare the performance of two persons with respect to the marks obtained in different subjects on average. So these are the basically test for the means perspective. Similarly, when we are saying equal variance or non-equal variance, that means we are talking about the homogeneity as well as the heterogeneity tests. So that means is the both groups has same variance or the equal variance or not. So then if the data is normal, we can apply the F test to check the equality of the variance. But if data was non-normal, then we will apply the Levene's test. But here in this video, I'm going to talk about the F test only, like how we can apply the F test using R. So in order to do that, to test the two sample independent t-test as well as two sample independent t-test when the variances are unequal, for that I have taken the example of this one, and the example is we have taken the 20 patients data about the hospitals, and we have taken the data of patient satisfaction rating of the two hospitals. So that means here in this case, as I told in previous videos, like always see your question or your problem with respect to X into Y sense. So X would be considered as a factor and Y would be considered as a measurement value. So right now Y is your rating, right? Y is your rating and X is basically the hospital type. Okay, hospitals. So and hospital type we have two types. So right now we want to compare is the mean of the hospital A is equal to the mean of hospital B, or the alternative is the mean of hospital A is not equal to mean of hospital B. So this thing also can be written as H naught mu A minus mu B. So that means the difference between the two hospital rating is 0, and alternative would be A is difference is not equal to 0. This is the two-tail test. Okay, it could be one tail, could be less than, could be greater than form, but right now the scenario is we are interested in the two-tail perspective. So two-tail mean is there any difference between the two hospitals or not? Okay, so right now we are not saying that a particular hospital with respect to the patient rating is better or less. We just want to check is the on average with respect to the patient satisfaction rating, the two hospitals are equal or not equal. So in order to do that, so I'm using R to apply this test. So first of all, I need to import the data set, and the import data set which I am using is the hospital comparison. So in order to import the data, what I will do, I will go to the environment, import data set from Excel, browse, and then I will go to the directory where I have put the data. That is over here, hospital comparison. Okay, so when you import the data, you will see Excel, R will automatically run the commands that it is calling the library of reading the Excel file, okay, as well as loading that library, or you can say the package, then saving the entire data set in a variable called hospital comparison. So whatever the file name, it will save in the name in the same variable. Okay, so whatever the file name would be, so what R will do, make a variable of the same name of the file, and this all the data will be stored in that variable. So as well as we are saying view this data set, so we want to view this data set as well. So if I click import, now we can view the data set as well as this data set we have imported. So the first thing we need to do is, once we import that, now we need to attach this data set because we want to use this data set. So in order to use, so we need to attach this data set. So the first thing, the first condition, as we have seen, in order to apply the t-test, two independent sample t-test, we need to check the normality of the data. So first thing what we are doing, this thing we already done for the previous test as well. If you can watch my previous videos. So the first thing is what I am doing, I am partitioning the page in 2 by 2. In 2 by 2 means in 2 rows, 2 column. And the first thing we are plotting, that is simple index, as well as on y-axis we have the actual data values. So we have total 40 data points, 20 for hospital rating A and 20 for B, right? And both are independent. And then we are applying the histogram to check the normality. It seems look like a normal, as well as we are applying the normal probability plot, which is QQ plot. Okay, so with the help of QQ plot as well as histogram, we can see that is the data follow the normal distribution, but this is purely a descriptive approach. From the QQ plot, we can see that if the dotted points lying on the straight line, which is a normal probability plot, then we will say data follow the normal distribution. As well as if the histogram is following a symmetrical curve, then we will say data is normally distributed. But remember that we can only hypothesize that this data may follow the normal distribution using these graphs. But for that, as I earlier told you in the previous videos, so we have some sophisticated methods, or you can say sophisticated tests, like Anderson-Darling test to check the normality. We have Kolmogorov, we have Shapiro test. Okay, so we can apply this particular test on the variable called, that it was rating, which is a numerical variable. So if I run this test and I can see the result that the p-value is 0.56. So that is indicating except H0. So when the p-value is greater than your pre-decided alpha value, okay, so the p-value is greater than or equal to your pre-decided alpha value, and right now the p-value is 0.5637, whereas your alpha is, let's say we are considering 5% alpha, so this is p-value is greater than or equal to the alpha value, so we will say except H0. Okay, so except H0 mean, that means data follow the normal distribution, because in any normality test the H0 would be equal to, we will say data follow normal distribution, whereas H1 would be equal to data do not follow the normal distribution. So because the p-value is greater than, so we will say except H0, that means data is following the normal distribution. So the first you can say assumption in order to apply the t-test is fulfilled, that is data is following the normal distribution. And the second thing we need to test is that we need to check is the variances are equal or not equal. That means we are going to apply the homogeneity test. Okay, so in order to do that, so we can apply the equality of variance tests in such test. So that means we are going to apply the F test because data is following the normal distribution. Okay, so in order to apply the F test, so basically our H0 is sigma 1 square is equal to the sigma 2 square. Okay, and the alternative would be sigma 1 square is not equal to sigma 2 square. So that is basically the homogeneity test. We need to check is the population variances are equal of both the groups or not. So same test can be written as, so that is sigma 1 square divided by sigma 2 square is equal to 1. Okay, means the ratio of the variances are equal to 1, whereas alternative hypothesis would be equal to the ratio of the variances is not equal to 1. Okay, so in order to apply that test, we will use this command, that is var.test. Basically this is variance.test, and then the first variable we will use, that is a quantifier variable, that is a numerical variable, so which is rating, then tilde sign, and then we will use hospital, which is basically the factor. So if I run this command and I got the result, if I see my p-value, and the p-values are indicating that this is 0.07. So again, this is greater than or equal to your alpha value, which is 5%, right? Because right now the confidence level is 95%. Okay, so that means our alpha is 5% by default. So if the p-value is greater than your alpha value, we'll say except h0. So that means both the population has equal variance. So that is homogeneity condition is fulfilled. So for our problem or our data set, the normality condition is fulfilled because the p-value is greater than the pre-decided alpha value, which is 5%. And according to the f-test, we got the result that the variances are equal. Okay. So that means homogeneity condition is fulfilled as well as normality condition is fulfilled. So now we can apply the two sample independent t-test by assuming that the variances are equal. So in order to do that, we can use the function called t.test. Then our numerical, or you can say the variable, the quantitative variable, which is rating, tilde sign, and then hospital. And then we will write down var.equal is equal to true. That means assume that the variances are true. So if I run this command, so we are getting the two sample independent t-test results, where the test statistics result, we got the degree of freedom result and the p-value. Okay, so right now how you will read this p-value? This p-value is quite small p-value. So this would be approximately equal to 0.00. So we got 6 zeros and then 213 something. So this is the p-value, right? Because we have the -7. So which is less than 5%. That means reject H0. That is indicating both the reject H0 means both the hospital does not have the same. Both the hospital do not have the same patient satisfaction rating. So one of the hospital has higher rating compared to the other, which we can also see that from their mean values. So if you can see that the hospital mean value is 8.3 and hospital B is 59.3. So maybe possible we can make the conclusion over here that with respect to the patient satisfaction rating, hospital A is performing better than compared to the hospital B, right? But suppose if you want to find out the two sample independent t-test by assuming that the variances are unequal in R, so how you can do that? Just because by default it will assume that the variances are not equal. So I will omit this condition. Okay. So if I run this command, so it will automatically apply the Welch approximation. Okay, by assuming that the two sample independent t-test means the heterogeneity condition means the variances are not equal. By the way, for this particular data set, the data was normal, the variances are equal, so that's why we can apply the two sample independent t-test. But if the data was normal and variances are unequal, then we can apply the Welch approximation, and the criteria in R to apply the Welch approximation is this one. Just skip this command. Okay, now I am detaching this data set because I don't want to use this data set more. So just I have detached it. Right, G? Okay, so the next test we are going to apply, that is called as testing of hypothesis for two paired samples. So this is also known as the pair t-test, means when the two groups are dependent. Like we have taken the sample before something, and then on a same group we again take the data set from the same sample, you can say from the population, that is such as before and after sense. You can also consider like the example of, for example, we are saying we have the 10 machines and we have taken the data set of the production rate of those 10 machines, and then we have done some maintenance program on those 10 machines, and again we have taken the production rate on those 10 machines to check is the maintenance is significantly impacting on the production rate or not. Okay. Similarly, you can say that if I'm taking the example of pharmaceutical company, suppose we have selected 20 patients and we have given a medicine to test is the effect of that medicine on those 20 patients is there or not. Okay. So, for example, that medicine is with respect to the headache medicine. Like we have selected the 20 patients and those have the headache. So the seriousness of the headache, and then we have given the medicine to those patients. So before the seriousness of the headache and after giving the medicine, the seriousness of the headache, in order to understand the effectiveness of that particular medicine. So whenever you have the pair form data, before and after sense data, then we can apply the two sample pair t-test, right? Like for example, in this example where I'm going to apply the pair t-test, that is basically a psychologist want to determine whether a particular running program has effect on the heart rate. Okay, effect on resting the heart rate. So they want to check the effect of the running program. So they have taken the resting heart rate of each person's before running that program, as well as they have conducted a running program, and then from the same population they have taken the resting heart rate of the person's data. And now they want to check is that running program is effective or not effective. So in order to apply this the testing of hypothesis of mean for pair t-test, so the only assumption is that the data must follow the normal distribution. Okay, so in order to do that, first of all, I need to import the data set of that is resting heart rate, which I can go import. I have put in the Excel format. Okay, I can go there. The data is resting heart rate. Okay, import this data set. So this is the data set before and after the resting heart rate, and this is the difference variable. Okay, and then we can attach this data set. So right now what I am doing in order to apply the two sample pair t-test, I'm using only the simple t-test. And how I am applying that, I have already, as you have seen that we can apply this two sample independent t-test on a difference data. How I have computed that difference, that is basically, you can say we have the before the running program resting heart rate data and after running program, and then we have computed the difference. That is basically, if this is x, this is y variable, so we can compute x minus y. So instead of applying this data set, we can use this data set in order to test whether the running program is effective or not effective. How can I do that? So I can use h naught would be equal to mu d, that is the difference between before and after is 0, whereas alternative hypothesis, the difference is not equal to 0. So that means the running program has no effect, that is the h naught, whereas we are saying in alternative hypothesis that the running program has effect. So that means in a resting heart rate, there will be effect if we got to able to accept the h1. Okay, so in order to apply that, we have already attached the data set, and then now I'm going to apply on the difference data set the one sample independent t-test. So the one sample t-test p-value is indicating that because we have applied this test on the variable differences, that is before the difference between before and after. So the p-value is less than 5%. Okay, that is indicating we should reject H0. That means the running program is affecting the resting heart rate. Okay, so that is indicating that after the running program, the resting heart rate is improving. Okay, so that is basically the p-value is indicating that the H0 should be rejected, H1 should be accepted, which means again that this the pair t-test is indicating that the resting heart the running program is better for the resting heart rate. One-way ANOVA analysis using R. So basically, I will talk about testing of hypothesis when we have two or more than two samples and we want to compare them with respect to the average value. So for that, I'm going to use this example, which is basically the tensile strength example. So where we have the dependent variable, which is a y variable, that should be in a measurable form. That is basically in this example is the tensile strength of the paper in PSI. Okay, so that means we want to maximize, you can say, the strength of the paper. So that is our y, and the input factor, which should be in a nominal scale, that we have considered as a hardwood concentration percentages. So we are considering that is the hardwood concentration 5% would increase the strength of the paper, or is the 10% on average. On average, 10% concentration will increase the tensile strength of the paper, or 15 or 20. So that means we want to compare on average these four basically the hardwood concentration. So our H0 would be equal to, that is the average hardwood concentration at hardwood concentration at 5% would be equal to, sorry, the average paper strength at 5% hardwood concentration would be equal to the average paper strength at 10% hardwood concentration would be equal to 15% would be equal to 28%. And our alternative hypothesis would be equal to at least one of this population mean is different from the other. So now we are going to apply this example on R using R. So for that, so let me start with first of all, we are going to read the data set. So this code is doing what? In this code, the first line, basically, this first line is doing that we are going to read a CSV file. So that means I have saved the data set in a CSV file, which is a comma separated file, which is Excel file. So you can say, and you can save it into a comma separated file. And then I am calling a function called file.choose, where it will give me a pop-up menu where I can pick up the file in which I have stored the data set. And then header is equal to true means that the first row in the data set would be considered as a headers, or you can say the name of the variables. So, and then that entire data set, I'm saying after reading that data set, that must be stored in a variable, which the name of the variable is called as a PTS. So if I run this command, now our that is giving us the option where is our data set, that is basically the tensile strength, and this is basically in a comma separated file value. Okay, so CSV. Okay, so in the last videos we have discussed if you have the data in Excel, how you can retrieve that. So now I have taken the data in a CSV file. So press select the file, open it. Now we can see that this data set in a variable PTS. If I write PTS, then we can see that data set, right? As well as the next command, what we are doing, I am going to attach this data file with R. So that means once I have attached it, Now, after attaching this data set, I would be able to get the, you can say, okay, now I have attached this data set. Now I want to view this data set, so I can write down capital V view. So the data set, the name of the data set. So this is my data set, which I have stored in a CSV file. So the first variable is basically the factor variable, or you can say the factor, with having different types. We have 5% concentration, we have 10% concentrations, we have 15%, 20%, and against that we have written down the paper tensile strength. Okay, so the first thing I'm going to write, so basically this function of line is indicating, so I just want to check the hardwood concentration. So basically, is this variable is a factor, because we taking as a factor. So what's the advantage is that, because this would be as our x variable, okay, and the quantitative variable is basically the tensile strength. So that is basically the y variable. So I'm just checking, because as you know that for applying the one-way ANOVA, the dependent variable, the y variable, must be in a measurable form, whereas the input variable x must be as a factor. So we have checked that the hardwood concentration, this is a factor. Okay. So in order to apply the one-way ANOVA, the first thing we need to check is the dependent variable is a normally distributed or not. So as I told you in the previous videos, that for checking the normality, we can apply different kinds of tests are available. Like we have Anderson-Darling test, we have Kolmogorov, but here I am applying the Shapiro-Wilk test in order to check the normality. So this is the name of the test, that is Shapiro.test bracket. Then we will write down our dependent variable. Okay. So that is paper tensile strength. So if I run this command, so I'm getting the results of this normality test, and we can see that the p-value is greater than your pre-decided alpha value. So let's say we have taken alpha as a 5%. So p-value is greater than 5%. That means accept H0. And what was the H0 in a normality test? The data follow the normal distribution, whereas H1 is data does not follow, data do not follow the normal distribution. So because the p-value is greater than 5%, so we can conclude that data follow a normal distribution. So that is the first assumption is fulfilled in order to apply the ANOVA. The second assumption is that is the homogeneity of the variances. So we need to check is the variance between all four factors, or you can say all four levels are equal or not. If we taken as a 5% wood concentration, or a 10% wood concentration, or a 15% wood concentration, or a 20%, is the paper strength, the variation in the paper strength is equal or not. So in order to do that, we have two kinds of tests which we discussed using Minitab in the previous videos. That is, one is the Bartlett test, another is the Levene's test. So for Bartlett test, in first situation, we should apply the Bartlett test. If the data follow the normal distribution, then Bartlett test is more appropriate one. But if you don't know about the distribution of the data, or you can say data do not follow the normal distribution, then you can apply the Levene's test. Here, what I am trying to do, I will apply both the tests in order to tell you how you can apply these tests using R. So for Bartlett test, there is no package we needed. We can just write down Bartlett.test. Then we should write down the dependent variable. That is basically the quantitative variable. Then we have tilde sign, and then we should write down the input factor, which is a hardwood concentration. So if I run this command, I am getting the Bartlett test homogeneity variance test results. And what was H0? The H0 was the variance of at 5% concentration is equal to the variance at 10% concentration, as well as the variance at 15%, as well as variance at 20%. So all four variances are equal, whereas H1 is at least one of the variance is different from the other, or you can say not all variances are equal. So here what we are getting that D value is 0.76, which is greater than your pre-decided alpha. Either you can take 5% or 1%. So here we are taking as a 5% right now. That P value is greater than 5%. So we can conclude that the variances are equal. So that means from Shapiro test, we conclude that data follow the normal distribution, as well as from the Bartlett test, we concluded that the homogeneity variance condition is fulfilled. So that means variances are equal from the Bartlett test as well as from the Shapiro test. We get that the data follow the normal distribution. That means now we can apply the one-way ANOVA. But before that, let me apply the Levene's test as well. In order to apply the Levene's test in R, I'm using a package called CAR. So first you need to install this package, or you can install it. You can go to the package, install, write down CAR. Okay, once you select CAR, and then you can install. Because I have already installed it, I am just after installing it, you need to call it. So I am calling the package called CAR, and then I'm applying the Levene's test as well. So Levene's test is also telling me that because here H0 and H1 would be the same as the Bartlett test. So Levene's test is also telling me that the P value is greater than 5%. So that is indicating that the variances of all the population is equal. So that means homogeneity condition is fulfilled. Okay. So we tested the normality, we tested the homogeneity. Now we are going to apply the one-way ANOVA. But before that, let me draw a box plot. As I told you in the previous video as well, whenever you are going to compare two sample independent t-test, applying two sample independent t-tests or one-way ANOVA, it's better to draw the box plot first in order to just check the comparative average value of all the factors, or you can say all the levels within that single factor. So right now the factor is a hardwood concentration, and we have taken the 4 level of this hardwood concentration: 5%, 10%, 15%, as well as 20. So in order to draw the box plot, what we will do, box plot, then write down the name of the quantitative variable, which is a dependent variable, that is paper tensile strength, tilde sign, and then hardwood concentration. That is a factor. Comma, this is basically not necessary. This is just, we are giving the heading of this plot, that is mean is equal to, so whatever you will write, it will appear at the top of your plot. And then this column rainbow function will do what? It will give us different colors box plot. Okay, if you don't write down this one, it will give us in a black and white form. But so if you want in a colors form box plot, so you need to use column. So I'm using rainbow. So there are different functions. So right now I'm calling rainbow. So if I run this command, so now I can see that at different hardwood concentration levels, the paper strength. So now we can see over here that on average, it seems that the paper strength for different hardwood concentration would be different. Or you can say that the hardwood concentration percentage is affecting on the paper tensile strength. But this is basically the descriptive approach. So we can just hypothesize from this graph. Now we want to test this one. So if I want to test this one, I can apply one-way ANOVA. So in order to do that, so the function is AOV. Okay, that is analysis of variance. Then again, we will write down the dependent variable, tilde sign, independent variable, that is a hardwood concentration, which is a factor, which is a nominal scale value. And then I'm storing this answer of this one-way ANOVA into the variable called model. So if I run this one, okay, and then in order to get the result, we need to apply summary. Okay, so if I just write down model 1, so in that case, I am just getting down the hardwood concentration, sum of square or residuals and degree of freedoms, but I'm not getting the p-values. Okay, so in order to get the proper results, so we need to apply summary. So if I apply the summary, now I am getting degree of freedoms, sum of squares, mean sum of square, and then test statistics result, as well as this p-value. Okay, so in R, we are also getting triple steric, two steric, one steric, or there would be no steric. So triple steric, that is indicating this p-value is almost zero. Okay, so by the way, because the p-value is, in our case, we have considered alpha as a 5%. So because p-value is less than 5%, we will say reject H0. And that reject H0 means what? That means the paper strength is not same at every level of the hardwood concentration. So at least the paper strength is different from at least one of the hardwood concentration level. Okay, so once we got this, that the paper strength is not same at every level of the hardwood concentration. So now we need to first of all check the model adequacy. That means, is this ANOVA, we can rely on the result of this ANOVA results or not. So for that, first of all, what I'm going to do that, because there will be 4 different types of graph. So first, with the command of this line, I'm going to partition the page in order to plot 4 different graphs. If I run this plot, okay, okay, so with the help of this line, what we are doing that is partitioning the page in 2 by 2. 2 by 2 means 2 rows, 2 columns. Okay, so I run this command and then I will run this plot. Okay, so this is 2 rows, 2 columns. Okay, if I write down 1 comma 2, so that it might give us the error because we need 4 spaces for this graph. So this is basically the residual as well as the fitted value. So we have on axis we have the fitted value as well as on y-axis we have the residual, and same kind of graph we have seen in the menu tab as well. This is the normal QQ plot in order to check the normality of the residue. Okay, so the first thing is this look like that the residuals are follow the normal distribution? Yes, it is look like that the residuals follow the normal distribution. Remember that I have told you that one-way ANOVA model is, that is Yij is equal to mu plus rho I plus error. Okay, so right now we are checking that is this errors follow the normal distribution or not. So this is look like because all the dots are follow this straight line, so that means data follow the normal distribution. And the second thing is we need to check that is the residue are constant. Okay, so it seems that there is no trend. Okay, there is no peaks in the residuals, residual versus fitted value. So it seems that the variances are also the constant. Okay, so that means we can say that the this ANOVA model is follow the is the more accurate one for this data set, because the residuals follow the normal distribution, as well as the second thing is the residuals versus the fitted value must have the constant variance, which is over here. Okay, so once we get that results, the next thing is now I want to know we from the ANOVA we got that all the means are not equal. Now I want to check that which hardwood concentration level is different from the others. That means we want to pairwise comparison. Okay, once the ANOVA results is saying that all are not equal, so then we can apply pairwise comparison. So for pairwise comparison, we can use Tukey test. Okay. So here I am applying the Tukey test. So in how we can apply the Tukey test in R, you can use this function which is Tukey HSD, comma model 1, because we have saved the ANOVA result in model 1 variable. So that's why I'm writing down model 1, and then I'm indicating at what confidence level. Okay. So if I run this command, so I'm getting the Tukey test results, and this is indicating the pairwise comparison. So right now this is indicating that the p-value only for 15 and 10% are higher. So that is indicating that at 15% and 10% the paper tensile strength would be equal. But for others, we can see that all the p-values are less than 5%. That is indicating that every other level is different from the others. Only 15% as well as 10% hardwood concentration will produce the same paper strength. Okay. Furthermore, I can also draw the plot that is again par 1 is indicating now I want to draw only one plot as in a whole page. So that's why I've written down 1. If I don't run this command, it will again use this partitioning of the page. Okay, so right now I'm using that I want to draw only one, so that's why I need to run this command 1. Okay, so then I am running down the plot. So here what I can see that, okay, so I need to run this command again. Okay, so let me, okay, so right now what I am seeing that what I can see is this one. Just a second. Okay, so what I can get from this line, that is basically I am plotting the Tukey's HSD, which is this one. That is again the whole command, which is basically the Tukey's model 1 confidence level, the same command I have put over here. And then LAS1 is basically indicating how these x-axis and y-axis value should appear. So with writing down 1, the direction would be the horizontal. So you can try 2 or 3 to see what kind of direction you will see on the values of x-axis as well as on y. And then the color means what kind of color you want to see on the graph, that is red. So if I run this command, so I am getting that or you can say the Tukey's plot. So how you can interpret this plot is if this confidence intervals crossing this red line, mean if the confidence interval contain this 0 value, that means those two levels are equal. So right now we have seen in a Tukey test that 15% and 10% are equal. Rest of them are unequal. Okay, so that means only at 15% as well as at for the rest of them it is not equal. Okay, now what I'm going to do is, now I want to apply the mean plots, means mean plot with confidence intervals. Okay, so in order to do that, what can I use? I am using a plot called basically gplots. So again, you need to install this package first. So if I run this command, okay, and then I am using the function called plot means, and then paper tensile strength, that is a dependent variable. This is an independent variable, and then this is the optional. I'm writing down what should be appear in the heading of the graph, what should be the y-axis, and what should be the x-axis. So I'm running this graph and I'm getting the results like the box plot, but right now we are also getting the confidence intervals. Okay, so here we can also see that it seems that at all the levels of the hardwood concentration, the paper strength is not equal. So I hope you clear one-way ANOVA using R. As well as we have seen in the previous video while we were discussing this one-way ANOVA using Minitab, we saw that if the data does not follow the normal distribution, then we can apply the non-parametric test. And we have discussed that against the one-way ANOVA, the non-parametric tests are available, either the Kruskal-Wallis test we can apply, or we can apply the Moore's median test. And I told you that under what condition you can apply the Kruskal-Wallis test. If your data do not have much extreme values, then you can apply the Kruskal-Wallis test. But if your data contains the Moore's median, contains the outlier data, then you can apply the Moore's median test. How you can identify that do your data have the outliers or not? The best option is draw the box plot first. So if I draw the box plot, I can see that there is no outlier in my data set. At 10%, at 15%, at 20%, at 5%, there is no outlier. If there is an outlier in the data set, we must saw some statics. Okay, but if your data does not have much outliers, then we can apply the Kruskal-Wallis test. Okay. Okay, so right now this command is doing what? If I if I don't run this command, so basically the p-value give us in the scientific notations. Okay, as we have seen the previous one, like if I run this command, Tukey's test, so I might get the value of the p-value in the scientific notations, but by running this command options, this SciPen is equal to 999. So basically the benefit of running this command is now I will get the p-value always in a decimal perspective. Okay, by the way, the Kruskal-Wallis is basically also indicating, so remember that right now I'm using the same data set in order to just tell you how you can apply the Kruskal-Wallis test using R. So by the way, because we have already seen that this data set is follow the normal distribution, so that means we can apply the one-way ANOVA, so there is no need to apply Kruskal-Wallis test. But just to tell you how you can apply Kruskal-Wallis test using R, so I'm using the same data set. So the command for that is Kruskal.test. Then we need to mention the dependent variable, which was the paper tensile strength, and then we need to apply the hardwood concentration, which is a factor. And in between we have a tilde sign. So if I run this command, I'm getting the Kruskal-Wallis test, and the interpretation would be the same, like the p-value is less than, so we can conclude that the population means, right now means being medians. Okay, the population medians, because we are applying Kruskal-Wallis, the population medians are not equal at every level of the hardwood concentration. So if you want to apply the Moore's median test, then you need this package. Okay, so the command would be Moore.median test. Okay, so I have already installed this, so I'm just running this command, and the same kind of results we are also getting. Okay, this one is a new, we didn't discuss through Minitab, but if you're you are using the non-parametric test and you find that, like we have find over here, that on median basis, all hardwood concentration are not producing the same type of paper strength, then we can check which paper strength is equal to the other or which are different from the others. So for that, we can apply the post-hoc test for the non-parametric test. So in order to apply the post-hoc test for the non-parametric, we can apply either Dunn test or either we can apply the Nemenyi test. Okay, so the difference is, so the Nemenyi test basically can be applied, or you can say is more appropriate when your group size are not equal. Okay, but Dunn test can be applied when the group size are equal. Okay, so in order to do that, we need this again library, the package, for in order to apply the Nemenyi test, that is DESC tools. Okay, so if I run this one, and then so here I'm mentioning that X is basically indicating the dependent variable. Here I'm mentioning the second one is basically the independent variable, which is the hardwood concentration. And then I'm mentioning that what kind of, how we can calculate the p-value. Should I calculate the p-value with Tukey's method, or should I apply the chi-square method? So you can use any one. So right now I'm mentioning either you can use Tukey's method in order to calculate the p-value, or either you can use a chi-square. The interpretation would be the same. But remember that because the data is follow the actually normally distributed, so here this test is indicating that all the levels are equal except only the 5 and 20. Okay, all other levels are pairwise equal. Same is the case if you want to apply the Dunn test, that would also the same. Okay, so here in this, the only difference is in this method perspective. So if I run this command, let me run this command. Okay, what I am getting, I will get P unadjusted and P adjusted. So the answer is same if I'm using none. So that means I'm not using any correction method right now. So the correction method, in order to check, calculate the p-value, so we can use the Bonferroni correction method. So for that we can use run test, and now you can see the p-value with unadjusted is different from the p-value with the adjusted values. So I hope you understand how you can apply the one-way ANOVA as well as the non-parametric test against one-way ANOVA, which is Kruskal-Wallis and Woods median test, as well as the multiple comparison in the form of non-parametric test. See you in the next video. Thank you so much.